Welcome to video 8-2. We're going to finish up chapter 8. We're going to try to keep the momentum going where we were lean last time. I think it was a relatively short video. I think we got right to the point, but said some important things to help you make sense of how lean accounting differs from traditional accounting. And we have maybe a little bit more to cover in this section. I just couldn't chunk this 8.3 section in half somehow. If I could have, it would have made the two videos a little more even. But we'll also try to be as much as we can diligent about reducing waste in the video of this chapter, unless it's really funny. Then we're gonna keep it. But that's one of the it's a value. That's the value of this video. It's one of the things that I bring to the table. So anyway, we have just-in-time inventory. Look. Inventory is waste. Lean says that a lot of inventory is waste. A lot of the times you're holding on to inventory, we have carrying costs, we have the cost of the warehouse, we have the cost of obsolescence, we're running lots of risks when we have inventory. And so, yeah, got a lot of lists of inventory costs right here. And so we shouldn't be storing large amounts of inventory. That is a wasteful cost. That's a prime target right here, something that drives the cost function up but does not really drive value for the customer. I mean, when was the last time you went into a store and said, well, I'll buy it, but only if you have 5,000 more of them in your warehouse? I don't think that's the case. I mean, unless you're Batman, you don't order them in buckets of 10,000. So with just-in-time, we have, again, this is similar to the first video. I'm not going to be able to cover everything that's entailed in the lean philosophy or in the just-in-time philosophy, but the two go hand in hand. They're not synonymous, no, but they go hand in hand. Lean companies often use, most lean companies adopt or move toward at least a just-in-time model of production. What that means is we're not holding on to inventory. If you don't have a big warehouse full of finished goods inventory, then you have to produce just-in-time. You have to produce at the moment you receive an order. You don't have a warehouse. You can just say, well, we'll ship it from the warehouse. So that's just by definition. If you're going to reduce inventory, you're going to move more towards a just-in-time model. Now, the just-in-time model reorganizes the production department into atomized cells, and the work does not start until it's pulled. A customer order pulls it across the production department, or through the little mini departments in the atomized cell. Within each cell, we usually have a cross-trained team of workers who work to be as fast and defect-free as possible. They have often they'll be empowered as much as possible to make improvements to the process because they're frontline in seeing the process and where it fails. And of course, defect-free is important because, again, you don't pay extra as a customer for defects. You wouldn't want to pay extra as a customer for defects. And so, rework is a huge source of waste. So what does this mean? Well, if we have a just-in-time philosophy, then we're probably going to want something more along the lines of a backflush costing model. All right, so we have that handy illustration. Again, we have cost accumulation method. Where are we accumulating costs? Well, we can accumulate them in COGS. Yeah, that's what we're saying. We're going to accumulate the costs in COGS and not trace it at all to individual product units until the very end of the period. Almost always a backflush system is periodic, and it says at the end of the period we have 5 units in inventory, some small number. And since we have such a small number in inventory, we're not going to. It's not a value to us to keep a perpetual inventory of them and trace costs like we do in the other paradigms. And backflush, we're gonna flush the costs back from COGS into the inventory accounts to represent those small amounts of inventory that are existent at the end of the period. And so, I'll often make, as tastefully as I can, jokes about a toilet here. We're flushing costs backwards. And you don't do that till the end of the period. So here we go. It can be paired with any inventory valuation rationale. We focus on 2 in particular. It's going to get its biggest bang for the buck with these 2 because this is just how lean firms want to think and how they want to incentivize production. If you don't have these 2, you are incentivizing overproduction is their argument. All right, so the idea is we're going to the backflush backflush is actually referencing the journal entry that credits cost of goods sold and debits inventory accounts, because during the period when you incurred actual costs, they were debited directly to cost of goods sold. So the debit was to cost of goods sold, and the credit was to accounts payable or to cash, if you paid with cash or on an account, depending on that. So the debit just goes directly to cost of goods sold. And at the end of the period, we actually didn't sell everything. We have a minuscule number of units in finished goods, a minuscule number of units in process, and then some little bit of inventory in the warehouse, some direct materials that are on hand. And we just need to carve a little bit out of cost of goods sold to go back to there. We have, for example, purchase of goods, debiting cost of goods sold, crediting accounts payable. Using labor, debiting cost of goods sold, crediting wages payable. We have some machine maintenance. We're going to debit cost of goods sold and credit the wages payable for the maintenance workers and the accounts payable for the supplies. At the end of the period, we do a physical count of the inventory accounts, depending on what we maintain as inventory accounts. Another point right here we'll get to. And then we credit that amount to cost of goods sold, because we're moving it back. We're back flushing it from cost of goods sold back to the inventory accounts. Now, what inventory accounts do we have? Here is the full gamut of a typical backflush costing system. These three right here. We have 3 inventory accounts. They don't look like what you think they would look like, because we're used to having a raw materials or direct materials account just for the warehouse for materials, and then we have a work in process account, a WIP, and then finally we have a finished goods account. Finished goods. The name speaks for itself. We often change that in a lean backflush system, because you don't really care about making these distinctions between materials that are raw and in process. And so you will say we're going to have a raw and in process account for materials. It's going to cover all the materials once we bought them until the time that they're in finished goods. So it's the warehouse piece, and it's also any materials in process. And then separately, we might have a conversion cost piece, which is about all the costs that we incurred with direct labor and overhead, the conversion costs. And then, for the goods that we have produced but haven't yet sold, which should be a small number because, we're producing them just in time, we need to get them delivered as quickly as possible. We shouldn't really have them sitting around in a warehouse for very long. We do have a small amount that we can put right there. This is the same as in a traditional sense. These two get changed. Now, this is one of the similarities between backflush and lean systems and process costing, a simplified version of process costing. But here we have a materials account and a conversion cost account. Wow, that lines up a lot with how we created the rates in process costing. But you know what? We're going to simplify so much. First of all, no equivalent units business. We just use a physical count of units. Often, almost always, lean firms. I won't say almost always. Often, lean firms will just say, "Who cares? If it's in process, we're just going to give it a full unit's worth of cost." And then that means that units, the equivalent unit, you don't have equivalent units that differ between direct materials and conversion costs. And so it becomes really easy. Your units in process are the same for direct materials and conversion costs. There is no non-uniform consumption, like we talked about. That gets rid of that entire problem. We do not have a special carve-out for beginning WIP costs. We don't care, because it's very unlikely that we're going to have any beginning WIP costs carried over from period to period anyway. We have such a small amount of inventory. We should be going through our inventory amount over and over and over during the period, just constantly turning around goods, sending them to customers as quickly as possible. That's the idea. Also, because value stream costs are aggregated at the value stream level, a value stream case take the customer from order to delivery, and we don't have transferred in costs. So yeah, just in time tends to say we don't need these separates. No, further up. We don't need these separate production departments that are going to be these big, monolithic, often ossified and competing departments that they're going to transfer costs between each other as it rolls along the process. No, let's just have an atomized cell that has all the different processes that it needs, as many as possible anyway, within that cell. And then when it's being worked on in the cell, and once it's done, it leaves the cell. So we don't care about transferring costs. We're not going to have any of those, because it's just not how our setup is, in a just-in-time system, a lean kind of system. Now, actually, a firm can even ignore, and if the costs are so minuscule, they might not even backflush actual costs and say, we have a standard, and as long as the standard is relatively close to where the actual cost would be for direct cost per material unit, or direct labor or whatever, conversion costs, then we're going to go ahead and just backflush the standard amount, and we don't need a very careful accounting of these very small inventory accounts, because we don't want to emphasize the value there. We don't want to waste the money creating that information. All right. Yeah, very, very important sentence for everything that goes here. Like I said, there's a lot of disagreement about within practitioners about what you do in a lean accounting setup, but there are many variations possible. But the rule of thumb prevails that the simple and non-technical is preferred over the complex and the technical. So if your friend on the floor or your engineering friend couldn't figure out the calculations or understand what you're doing, then you probably would not want to do it, which is the case with a lot of process costing rigmarole, and so we've gotten rid of a lot of that right here. Simplify it. Let's backtrack and look at a quick example of that simplification. So this also helps us introduce the idea of direct costing. We start out with the assumption of direct costing, which is that we only consider DM, DL, and variable overhead to be product costs. Those are the only costs that we're going to be putting into inventory accounts. So the idea is we just take the actual costs, and we are going to average these, the average cost of direct materials, the average cost of these two together to be conversion costs, just like we would, or similar to how we would in process costing. Take the average of those and divide them by the units to get a per unit cost, and then we're going to apply that to the different inventory accounts that we're backflushing to. So let's say materials cost is $500,000. Our direct labor cost is $450,000, and the variable overhead cost is $50,000. Look at that. The math. That math looks really good. Almost like someone made this example to order. Yeah, we have 10,000 units total. This is just our total count of units that are in process and that got completed, whether they were sold or not. Just total units that had work on or had anything done with them this period. Now, direct materials cost per unit is just that $500,000 of direct materials cost over that 10,000 units. And we get $50 per unit for direct materials cost. Conversion cost is the sum of the two conversion costs, so $450,000 here plus $50,000 to equal $500,000 over the 10,000 as well. So we end up with, it doesn't have to work out this way, but it did because I made the example this way, $50 per unit for conversion costs and $50 per unit for direct materials costs right here. So the overall unit cost is $100 per unit. Okay, now we figure out the backflush entry like this. We also take account of raw materials and see that there's about $1,000 worth of raw materials in the warehouse, and we count 120 units in process and 130 units that were produced but not yet sold or not yet shipped or whatever line of demarcation we use for that. They're going to be finished goods. And so our backflush entry uses this number and these numbers if needed, as needed. And multiplies them by in process and finished goods. So first of all, we have $100 per unit and 130 unsold units. They received the full unit treatment here. They have all their direct materials and all conversion costs in them, so we're going to use the full unit cost right here times the 130 unsold units. So $13,000, which is that 130 times 100, is going to be debited to finished goods. We're bringing that out of COGS. So right now, COGS would be $13,000. That's what all we were doing. So a credit to COGS of $13,000. Debit to finished goods of $13,000. We'll just treat this as I'm explaining, a voiceover here. I'm just explaining this as a running tally. Not yet $26,000, but we'll get there. Raw and in process. So we're only talking about materials here. This is the RIP account, raw and in process, RIP. The in process part of that is 120 units that we're going to consider completely done with regard to materials cost, because remember the conversion costs are on a separate inventory account. So $50 times that 120 units gives us $6,000 for the in-process portion of the RIP account, the raw and in-process account. We also have the raw portion, which is $1,000. So that $6,000 plus that $1,000 gives us the raw and in-process debit of $7,000. And so now we have a running tally. We're crediting $20,000 to COGS to get $13,000 debit to finished goods and a $7,000 debit to RIP. And then we have, lastly, a conversion cost inventory account, assuming our firm in this example uses all three of these often seen lean backflush inventory accounts instead of the more traditional 3 that we were used to seeing in previous chapters. With conversion costs, we have our $50 per unit conversion cost times the 120 units in process, and that gives us just the $6,000. And so that's how we end up with a total credit to COGS of $26,000. And so we put all of our costs, all $1 million of our costs, our product costs, into COGS during the period as those actual costs were incurred. And then we're only taking back out, crediting out $26,000 of that. And so that leaves $974,000 debit balance left in COGS of cost of goods sold this period. So that's pretty good. That's pretty good. Given that we had $1 million worth of costs and 10,000 units, we have only $26,000 worth that are stuck in the inventory process. That's pretty lean. That's good. We don't want a lot stuck in the inventory process. We make money off of things that are sold and shipped out. And so that's a good example there. Now, let's go back to the fundamental. That's a good example of the backflush kind of process as it goes. That would be done after the period's over. Almost all, very often, if not almost always, backflush systems are periodic, and so therefore they're not doing this instantaneously. In fact, that's going to be the assumption if I ever give you a problem on backflush, that it's a periodic system. They go hand in glove here. Now, so like I said at the beginning, we have this assumption that we're excluding fixed overhead. This is the traditional setup that we're used to from Chapter 4 and Chapter 6. Omitting for a second Chapter 5, it's kind of goofy. Activity-based costing can be kind of goofy. Leave that alone for now. In our traditional sense, we consider product costs to be the direct costs, which are direct materials and direct labor, and all overhead costs. And overhead includes some fixed and variable portion, oftentimes. Here, we have intentionally excluded fixed overhead, and there's a reason for that. The reason is direct and variable costing. Many lean firms lean on that because in traditional costing, in which you would include fixed overhead and absorb it into inventory, which is the same thing as saying considering it a product cost, there is an incentive to overproduce. And I'll show this in the images that follow here. And so here are two different types of income statements at the bottom. I want you to focus on the bottom here. You can look through the textbook and see how the spreadsheets work on your own, the upper parts here. But I want to focus on the bottom here. If we use traditional absorption costing, we end up with an income statement that looks kind of like this. Let's just say we're the factory, and we're just looking at our factory's income statement. And we have sales of $60,000. We have cost of goods sold, which is going to include our direct costs and both types of overhead. This is the traditional way of looking at it. And then we end up with the gross profit number. And then we have some operating expenses. Typically, I've gotten rid of those for this example because it doesn't make a difference. Direct costing doesn't differentially treat the traditional operating expenses. They're still exactly the same place. They'd be right here between row 15 and 16 on the direct costing side, and they'd be right here on the absorption side. But I put them 0 just for simplicity's sake. So the operating income is $22,000. Under the direct costing side, because we have not considered fixed overhead to be a product cost, it's never going to be sent to an inventory account. It does not. That fixed overhead cost doesn't go into work in process, doesn't go into finished goods, and it's going to be registered almost as an operating expense. In fact, I think it would be fair to say it's considered an operating expense. So direct costing takes sales, takes cost of goods sold, which are all variable costs now, often anyways, assuming direct materials and direct labor are variable costs. More on that assumption when we get into the last part of Chapter 8, but for now. And therefore, we have set up where we now can get total contribution margin, because that's what contribution margin is, right? Revenue minus variable costs equals contribution margin. So instead of gross profit, we'll label this contribution margin, and then we subtract away the fixed costs, and now we have an operating income. This looks very similar to what we had in Chapter 3, where you're looking at these first 3 lines are encapsulated in the CM ratio number, and these last 3 lines overlapping at contribution margin are encapsulated in the degree of operating leverage number. So regardless, what we're going to see is that right now we're producing the same number that's sold. I'm the manager of this factory, let's say, and I truly believe that there's 1,000 units of demand, and I'm right. There are 1,000 units of demand out there. Now, let's say $22,000 of operating income, or $22 million. If we're in thousands, let's just keep the numbers smaller for our sake. $22,000 of operating income isn't enough to make my bonus. let's just say I need to kick it up a notch. Well, I could do hard work, like figuring out where we're inefficient, trying to train workers better, trying to set a better example, whatever, the hard stuff. Who wants to do that, though? Or I could overproduce and just find an excuse or communicate an expectation that's undue, that we're going to have 250 extra units of demand, and convey to the factory that, I think we're going to sell 1250 here instead of just 1,000. And so we're going to produce 1250. Well, that'd be wrong. And so we're still going to sell 1,000, but we produce 1250. So we have 250 units that are produced but not sold. Now, where are those represented on the balance sheet? They're represented in the inventory accounts. They'd be in the finished goods inventory account. Now, notice what I'm doing here with the fixed overhead cost specifically. This is where direct or variable costing, it's sometimes called direct costing, this is where direct costing diverges from traditional absorption costing. When I overproduce under traditional absorption costing, I'm taking this $20,000 of fixed overhead and dividing it over 1,250. So each individual product gets a smaller share of fixed overhead. Now, the number of units sold, 1,000, is the same. And so this is the number of units that's going to reflect how much of that fixed overhead goes to cost of goods sold, which is the only thing showing up on the income statement under absorption costing. And so I have, by virtue of division, decreased the fixed cost per unit for the units sold. And so I've moved that down by $4,000. Used to be $38,000. Moved it down by $4,000. If you really want to get into the weeds about that, it's through this. It operates. It passes through at the very least. It's not because we're doing this, but it passes through the overhead control account. We produced extra units, so we over-applied overhead. We've got to take that $5,000 and rejigger it. You got to move some of it to, remember for Chapter 4, there are two ways you can close out that account. You can either push it all into COGS, which would be even worse than the example I've given you here. I've given you the best case scenario in which you distribute it ratably and you push some of it into finished goods and the rest of it as a credit to COGS. Some of it as a credit to finished goods and some of it as a credit to cost of goods sold. And so that credit actually ends up being the exact amount that we're reducing the cost of goods sold amount. But don't get bogged down in those mechanics. What's happening overall is that this fixed overhead number, is being divided into smaller pieces because we produced more for that fixed overhead amount. And so therefore each product unit has a smaller share of fixed overhead. And some of those product units, 250 of them specifically, are stuck on the balance sheet. And so they haven't yet seen the income statement. They're stuck there. We're playing the system. And there's an incentive to do that. Maybe that gets me my bonus. 26,000? Yeah, now I can buy that fishing boat or whatever. I don't know what I'm going to do with the bonus money. Let's say I really screwed up and I'm very far away from my bonus, and so I want to overproduce a lot to save that fishing boat. So I'm going to overproduce by 1,000 units. This is just doing the same thing up here, but at a much larger scale. And so now we're going to divide that 20,000, effectively is what we're doing, by 2,000, 1,000 extra units from what we expected, what really we have demand for. So we have 1,000 units sitting in finished goods. Okay, so yeah, like I said, we're going to divide this 20,000 by 2,000. And so now each unit is getting effectively $10 worth of fixed overhead. And only this 1,000 units worth of it, $10,000 total, is going to see the income statement. It's going to hit the income statement because cost of goods sold reflects the cost of goods sold. The 1,000 goods sold is the same, and now it's only receiving $10 per unit. It's because of the finished goods. The fixed overhead is being divided over extra units in finished goods and the units that are sold. So yeah, we end up with now 32,000. Oh man, I can buy 2 fishing boats. I'm set. I'm going to go into the shrimping business instead. Why even stay here at the factory? So yeah, we've got 1,000 units that we overproduced, and so we have increased our operating income. Well, what has been happening over at direct costing? Nothing. This number, this number, this number, this number, and this number are all the same, no matter how much we overproduce. Look at this. This is just we're producing at demand. Now we've overproduced by 250. Look, the operating income stayed the same. All the numbers have stayed the same. And now it's the same, even though we overproduced by 1,000 units because direct costing cut out the fixed overhead, which is being sliced into smaller and smaller pieces so that a larger share of that can go onto the balance sheet and not hit the income statement. Because we did not consider that a product cost, we have reduced or eliminated the incentive to overproduce. And so that's why lean firms like direct costing. And oftentimes, the assumption when you go into a backflush system is that you're going to use direct costing. And you're not going to consider, right here, you only consider direct materials, direct labor, and variable overhead to be product costs. Now let's talk about time-related waste. And I hope your comment to that is not, like this video. No. Let's be serious here. I'm always very serious. Time-related waste is the basic idea that we have every company has an important resource, and you can waste it. And that resource is time. Every company, every worker, every machine is given the same number of hours in every day, and the same number of days in every week, and the same number of weeks in every year. And it's given that every time you have a free spin on this rock circling the sun. So when you don't match your capacity, the potential, it is idle capacity, and that is waste, according to lean companies. And so what we're going to talk about in 8.4.1 are different measures of capacity waste. We have 1, 2, 3, 4, 5 different measures of capacity, and therefore we're going to have 1, 2, 3, 4 different variances that we can pull from that. We can take this minus this, this minus this, this minus this, and this minus this. That's 4 minuses that I just said. So we had 4 variants. Look at that. That replaces variance analysis for many lean firms. They look at the differences between capacity numbers as a form of variance analysis. Capacity is the amount of work you can do in a given period of time. Again, time is the constraint. We're going to try and maximize how much bang we get for our buck, how much we don't waste the time that we're given. It's a resource that we're given every single sunrise. Let's start with theoretical capacity. And I'm going to take the example here and I'm going to expand upon it. So in the textbook, I only have this example under theoretical capacity. I don't think I have it anywhere under the other capacities, but in the voiceover, I'm going to go ahead and carry it out through all of them. So theoretical capacity and practical capacity are starting from the theoretical maximum you could possibly have of capacity given the time constraint. So theoretical capacity is to say 24 hours in a day, how much could the machine or worker, or in my analogy here, student, get done in 24 hours. Now, theoretical capacity has that important adjective of theoretical because it's not achievable. But we want to find what the endpoint is so we don't set, for one thing, unrealistic expectations. If we literally couldn't produce more than this given the time that we have, why would we even set our aims there? So we want to make sure we have the ceiling. And over time, it's a critical thing, over a period of continuous improvement where we will try to move closer and closer to that theoretical maximum, but we might never reach it. That's okay. Let's at least define what it is. So if we assume that there are 24 hours in a day and each class meets for 1.5 hours a day as a student, then your theoretical capacity for learning each semester is 16 courses. Wow, don't you feel lazy? You aren't taking 16 courses this semester, are you? You're not reaching the theoretical capacity of your learning, are you? Now, this is also keep in mind now with my example simplified, and I'm assuming 1.5 hours a day. That's not your typical 3 credit hour class. Your typical 3 credit hour class meets for 1.5 hours 2 days a week. This is assuming you meet every single day. So these are super classes. I don't know, 10 credit hours a class or more. And you're taking 16 of them. You're basically in a semester complete more than a bachelor's degree worth of learning. So it's almost always unreachable. But we want to know what the ceiling is. Literally, given the structure of the fact pattern, the maximum we could have is 16 courses a semester, given these mega credit hour courses. Okay, well, let's step one step away from that, still in the theoretical realm, but let's modify our math by subtracting some reasonably necessary rest and maintenance. So let's go ahead and assume, I'm going to, like I said in the voiceover, I'm going to continue with this example even though it's not here anywhere in this paragraph. Let's assume that you're a student and your capacity is capacity to learn. That's what you produce for the world or the company or your own life. The company, I meant the university, or your own life, in this analogy. And we're going to go ahead and say, well, yeah, okay, fine. You have to rest. So we're going to give you 8 hours to rest. And, the brain is a very calorie hungry device, organ in your body. And so you're going to get an hour to eat as well. So we're going to take away 9 hours from the day. So that's reasonably necessary rest and maintenance. That allows your brain to rest, recharge, lets all of the circuitry repower itself, and it gives you time to chow down and replenish those calories that it's burning. Okay, 9 hours out of the day are out of commission, and so we have 24 minus 9 equals 15. Now you have 15 hours in a day. We're going to keep with our assumption that we have 1.5 hours per day per class, and that gives us 10 classes per semester. Now, still, you're being a lazy bones here. What's going on? You're not taking 10 mega classes a semester. Okay, we're still in theoretical land. Even practical capacity is kind of impractical because it's built off of a mathematical equation, and mathematical equations by necessity follow pure rules that you can conjure that can be factored into the math. As it gets closer and closer to reality, it gets longer and longer. The equation gets longer and longer and longer, and incorporate more and more nuance, and becomes, in fact, ultimately, it becomes less and less usable. And so we really, even assuming some reasonably necessary rest and maintenance, we'd have to get much more specific. Okay, well, to get anywhere near what we actually take in a given semester, we'd have to include so many more assumptions about what kind of rest and maintenance you need. You need downtime because you're going to go crazy if you're working 15 hours a day on schoolwork, especially when you have somebody who's saying crazy things on an internet video. Yeah. Okay, let's jump. Before we talk about any of the differences between these, let's go ahead and talk about the rest of the definitions of capacity before we go to the variances between them. Next, we have normal capacity. And from here down, we're in reality. Here up is in theory land. It's all mathematical. Here down, it's measurements of reality. And so this is the big bridge between theory and reality. And often this is a pretty big difference between practical capacity and normal capacity. And normal capacity has this word norm in here, which I hope makes you think of the norm over a large scale of data. And so I'm going to pull this word out called empirical. These three are empirical. And when you get data, when you get actual observations from real life or the wild, it becomes empirical. When you're just sitting down saying, 24 hours in a day divided by 1.5 hours per day gives us 16, you're in the theoretical realm. You're using pure math, which is this pure, has these laws that can't be violated and so on and so forth. Whereas here you're saying, I'm going to look at what's really here and try to build up from there to get some sort of a norm, some sort of a general rule that applies. It's kind of if we're going to go back all the way to chapter 1, the prescriptivist, the descriptivist, working up from empirical reality up to bigger rules. So the normal capacity is how much you expect, stretching out across a few business cycles, a few cycles over the long term. You want to know how much actual work gets typically done. So you're gonna try to make sure you don't take just one period and say, well, last period we did this. No. Let's average over the last 5, 10, a certain number of years or periods, so that we smooth out the peaks and the valleys, and we get just on average what's our norm for capacity. Okay, we have, again, like I said, we're gonna have a big gap here when we get to the variance between these two. Okay, now we have budgeted capacity, which is the expected work, expected keyword, for this coming period, whatever however we want to place ourselves in time. But the idea is we have a norm, and then, we're going to set a budget for this period. Are we going to diverge from the norm? Are we going to go up or down in capacity? So let me go back to the normal capacity in my analogy. So the normal capacity is typically for undergraduate students, I'd say about, including part-time students, probably just south of 4 classes per semester. So I can include part-time students, just south of 4 classes per semester, and these are 3 credit hour classes that meet only twice a week for 1.5 hours. That's more the normal capacity, I'd say. And so our budgeted capacity then would be, well, what are we taking this upcoming semester? Is that higher than the norm? We're signed up for 5 classes if we're an undergrad or whatever the case may be, or maybe even 6. Let's go crazy. that we compared budget. It's pretty simple. I hope that's pretty simple. The idea is it's your plan, your expectation. It's informed by all of your expectations and mindset, all of the knowledge that you have accumulated to build some sort of prediction. Oh, well, next semester I have no internship, I have no part-time job, I can actually crank away at a bunch of classes, and they're easier classes, whatever the case may be. You have information that leads you to budget a certain amount of capacity for next period. So it reflects where you think you're going to go in the future. It reflects knowledge in the end. Budgets are in the end a reflection, at least partially, of knowledge. Actual capacity, last capacity that we have, which is normal capacity, but just for one period. For this period, what's the actual capacity of this period? What did actual work was done? And that's where the rubber hit the road. How many classes did I actually take this period? Oh, well, I planned 5, but I dropped one because this sounded like a crazy cost accounting professor, so I decided to take a different semester. So actual capacity was only 4. And now we're going to look at the differences between these 5 and come up with these variances that lean accounting uses to try to maximize the output of your firm given the constraint, which is another way of saying reducing the time waste, the idle capacity waste. All right, so I actually am pulling these definitions, and I'm giving credit here, these names for these variances, from a textbook called Management Accounting, An Integrative Approach. It's by McNair, Connolly, and Merchant. And so these 4 names may differ from people in practice. Like I've said throughout this chapter, people disagree about what to call things and how exactly you do lean accounting. I still think these are pretty useful, and these do encapsulate the 4 differences between the 5 ways of defining capacity. So the difference between theoretical capacity and practical capacity, we're still in theoretical land, in make believe, in the land of pure imagination, as you might call it. We have rate-based waste, and the reason for that is that we've changed the rate. This is based on the rate at which we have necessary rest and maintenance right here. And so we said that 9 out of 24 hours need to be rest in my example. I said, you got 8 hours of sleep and you need an hour to eat. So that's 9 over 24. 9/24 of the day is rest, is necessary rest and maintenance. If we could change that, we could move practical capacity closer to theoretical capacity. So in some distant future, try to be less dystopian about this than it probably will be. In some distant future, let's just say we have some machinery that helps us, or some biotechnology that helps us to get all the needs, the caloric needs that we have, and rest and recharge needs that we have in 4 hours instead of 9 hours, like I said before. And so now only 4/24 of the day are taken up in necessary rest and maintenance. And so your practical capacity is moving closer to the theoretical capacity. Now we have 20 hours a day, and I don't want to do the math on that. It's just south of 14 classes, excuse me. It's just south of 14 classes a day every semester, 14 classes every semester that you could take. So the theoretical capacity, the ceiling is 16 classes given 24 hours in a day. Because we've reduced our rest time that we need down to 4 hours a day, we now have moved from 10, which was our old practical capacity, up to just shy of 14 classes per day that we can do. So we've reduced rate-based waste, and over the long term, companies are indeed interested in doing this. You are indeed trying to squeeze more out of move your practical capacity, squeeze more out of the day in the end by moving your practical capacity closer to theoretical capacity. And the theory is that if you pull this closer to this, you'll pull the rest of the capacity definitions along with it. Maybe that theory doesn't hold up in practice, but the idea is even attacking this should move. In the end, normal capacity will be chained along and move up as well as you move practical capacity closer to theoretical capacity. I mean, think about it. You might not take 14 mega classes every semester if we suddenly had this dystopian future where we only sleep and eat 4 hours a day. You might not take 14 mega classes a day, but you might take more than 4. That might increase time. You're not going to spend all that time on video games, right? So you might spend some of that time taking an extra class or 2. So yeah, it will move up the rest of the capacities. It should, anyway. All right, so yeah, we reduce rate-based waste by reducing the rate at which our machinery, our people, and so on and so forth need to take necessary rest and maintenance. Okay, now the difference between practical capacity and normal capacity, like I said, there's often a very big gap here because we're bridging the gap between theoretical maximums, incorporating necessary rest and maintenance for practical capacity, and empirical reality. What do we actually do on average or normally? Using those two synonymously, normally and on average meaning the same thing. What do we do normally? And this is called management policy waste. At least these two authors call it that, and I like this term because it lays at the feet of management and their policies this gap. So the idea being that, at the very least, a part of that gap is due to management policies. So, for example, let's say, going to our class example, let's say that one of the things that management does, let's say university management, makes it very expensive to live on campus. They choose a variety of things that make it expensive to live on campus. And I'm not talking about tuitions specifically. Maybe I am as well, but let's talk about other things that they can do to make it expensive to live on campus. If campus policing is not done very well, then property crime could go up, and therefore there's an extra cost in terms of potential theft, also potential injury. Those are additional costs of living on campus. Let's say, for example, they drive out good businesses from campus and put onerous limitations on businesses that drives up prices on campus or near campus. Let's say just merely growth in the student body that's on campus will increase could increase prices around campus, and so you have to have more money to live on campus or to attend the classes, and so that increases the likelihood that you're going to want a part-time job, which will impede your ability to reach practical capacity. It will serve as part of the buffer between normal capacity and practical capacity. At least a certain number of students will want more of them will want part-time or even full-time work because these additional costs that nobody got time for that. Management policy then could help minimize the gap of that. And sometimes this works in a very counterintuitive manner. Management policies are. It's funny that I met. It's been a long time people have been trying to plan centrally plan things, and if there's one lesson we've learned is that there are a lot of ways to do it wrong and very few ways, if any, to do it right, and there are a few things that are rightly done that are the real purview in a pragmatic or even a theoretical and moral sense of central policy and planning. And so this is an example of this. I'm going to tell you a story now. A counterintuitive example of management policy driving, actually, in a way, moving normal capacity higher, at least on my end. So I was a student once. I was an undergraduate student at Arizona State University at the time when Michael Crow he's still president over there. He had this big initiative that he had called the New American University, which in the briefest terms possible meant charging a lot for tuition. That's basically the long and the short of it. The New American University was to make a public land-grant university like Arizona State very expensive. And so every semester, there was an enormous increase percentage-wise in tuition. I don't want to expose myself to more tuition cost than necessary, especially given how much of it is going to pure bureaucracy. I mean, the stack of papers I had to send in to prove that I was a resident of the state was Kafkaesque, let's just say. So I knew where my tuition dollars were going, and it wasn't necessarily a lot of it going, and a lot of it was not necessarily going to improving my education. So I said to myself, how quickly can I get through this? How short can I make this degree? And so on a personal level, their management policy here moved my normal capacity for classes up. I packed as many classes as I could each semester into my schedule. And so sometimes management policy works counterintuitively. You might think that increasing tuition you might think it's a negative thing, and therefore it will depress normal capacity. But for some students at least, it might actually make them move through the classes faster and say, I don't have time for any other stuff right now. I got to get through this because tuition is just going to rise in the future. Okay, anyway, let's move on to the next. So the difference between normal capacity and budgeted capacity is budgeted waste. That's fitting. And remember what I said. The budget is a vehicle for knowledge. I don't think I said it in those terms, but it is a vehicle for knowledge. It's associated with knowledge. It's based on knowledge you have of the future, your guesses and aspirations for the current and future period. I just read right there, read that phrase. And so the difference between what on average happens and what you're budgeting for this period or a future period is going to reflect some information that you have now, or maybe reflect the aims. If you don't set your aims high enough, this could reflect that. Why are we only projecting 3 classes next semester? Our norm is 4. Maybe we need to talk from somebody and learn to round up our shoulders and bear a meaningful burden or something. So this budgeted waste can reflect a more short-term management policy problem, a problem with our knowledge or expectations for the future. It could also encapsulate some real reservations we have about the future. Perhaps we're only scheduling 3 classes next semester because we're working full-time next semester. We've got an important job that will help us a lot with our future career, and so we're gonna taper back a little bit on the class end, and so therefore this is acceptable. But at least we have recognized that this is our waste of time, if you will, our idle capacity for learning, but we're using it somewhere else that we're thinking we're getting more bang for our buck. Okay, so we're using our hours elsewhere. They're not just idle capacity waste. We can say this gets offset somewhere else. And lastly, we have efficiency waste. This is where the rubber meets the road. We budgeted a certain capacity, and what did we actually accomplish? And so this is much more kind of, if we're just looking at it strictly from Chapter 7 point of view, this is more or less what Chapter 7 does. It says, well, what do we budget? What did we actually do? And it's split into different pieces, but that's the point. That this more or less is what we're talking about in Chapter 7. It has similarities at the very least. And so we have problems of execution being often what we have here. And so maybe it falls under management policies because management policies affect execution, but there are other things that go into it as well. So we have some often lower level personnel and operational decisions that affect this rather than the big picture management policies that we're talking about. That weird class, I was expecting to take it, but I dropped it, so that explains the difference between budgeted and actual capacity. And so now that we've talked about these variances that we use to consider idle capacity waste, let's take that to the next level, which is the theory of constraints. And the theory of constraints says, okay, we have the ultimate constraint, which is time, and there is some process, almost certainly, in our system that has the least throughput per time, and that is our constraint or our bottleneck or our capacity. Here we go. Capacity constrained resource, or sometimes capacity constraining resource. I think some people call it that as well. But the idea is this one process, this one step, this one class. I don't know if I want to carry that analogy any further, but the idea is we have some step along the way that really does limit how much we can do in a given period of time. And theory of constraints is all about how to maximize productivity, taking that into account. Okay, now the purpose of this lecture and this class and this chapter is not to teach you how to learn theory of constraints, although if I did, it would be time well spent for you and for me. It's just like the best thing in the world. But what I want to get down to is how this affects your backflush costing. So way up, I'm not going to get to it, but way up earlier in the chapter, I said that there are 2 different, or earlier in the video, I said there are 2 different ways that you change your costing. One is direct or variable costing. The other is through throughput accounting. Throughput accounting is a function of the theory of constraints. So hence the title and subtitle right here. And so this changes our backflush costing. So under the theory of constraints, what we do is we recognize that not everything is variable that says it's variable. In fact, in a lean environment, which is theory of constraints and lean go hand in hand, perhaps not as closely as just-in-time and lean do, but they're often used together, or at least they have very similar and parallel mindsets. And so in a theory of constraints mindset or a lean mindset, you actually don't consider direct labor to be a variable cost. Because your direct laborers, you're going to be investing more in them. You are not maximizing off of direct labor efficiency variance. You're getting rid of that variance, and a variance analysis in general. You're not trying to maximize, squeeze them for as much time as possible. You're not trying to get the cheapest labor as possible. You want to manage labor as if it's one of those X's, the inputs to the profit function that spans cost and revenue. Because guess what? Those laborers, the direct laborers especially, are producing the very thing the customer wants. And so they're definitely a cost that affects revenue and drives revenue. And so most all lean firms treat layoffs as very bad. They do not want to do that. And if you can't lay people off, then how can you say direct labor is variable? Because if your production goes down and you're not laying people off, you're still paying those people. You're gonna still have, furloughs can only last so long. You can't be having them on contract but not paid. That doesn't really work for the worker. They're going to leave. So yeah, if you don't want to lay them off, which you don't in a lean and often theory of constraints mindset, you really can't consider labor to be a variable cost. Likewise, you can't consider a lot of the variable overhead costs to be variable either. Now, there are some different reasons for this, but one of them is, theory of constraints recognizes that there's a much less precise relationship between variable overhead and actual production. It's overhead, so therefore we can't trace it, economically speaking, to individual product units. And so theory of constraints said, nope, that's not simple enough, that's not direct enough, not true enough. So the only product cost under traditional senses that theory of constraints and throughput accounting considers to be a product cost is raw materials. And because it says it's the only cost that varies with production. So production varies with production. So raw materials is the only product cost because it's the only totally variable cost with production. You have to produce a new table. That means you must have an additional X square footage of lumber. So it doesn't necessarily mean that with labor. Often people are on salary nowadays anyway. Even the direct laborers, they're on salary where they have union contracts. And so, yeah, your ability to vary the cost you spend on your laborers, much more restricted nowadays than when traditional cost accounting was produced back in the good old, cough your lungs out, black lung assembly line on the factory floor days. So throughput accounting says, hey, for our purposes, says we're only going to consider raw materials to be variable costs, and therefore they're the only ones that are considered product costs. And so, you know what? That simplifies our backflush entry. We're only going to backflush the amount we need to consider the raw materials that are raw and in process, and the raw materials sitting in the finished goods. We are not debiting to either of these accounts any direct labor costs, any conversion costs. We're just ignoring all of that. It makes it makes the calculation much simpler. We're also crediting much less to cost of goods sold. It is in many ways the end point of the reasoning of lean accounting. And for the final item, let's circle back to Chapter 3, as we do at the end of Chapter 8 here, and we say, let's revisit the idea of constrained decision-making with our new definitions from theory of constraints. So we've redefined contribution margin to include the idea that the only product cost, the only variable cost, is raw materials cost. And so unit throughput is now our new definition of unit contribution margin, because contribution margin was unit revenue. Well, unit contribution margin was unit revenue minus unit variable cost. And since we only have raw materials as our variable cost under a throughput accounting paradigm, then we can replace the unit variable cost with just the raw materials cost, because that's the only thing we think is truly variable. And so therefore this is more or less replacing unit contribution margin. And so back in Chapter 3 we said we had this very similar equation to right here, where we would take contribution margin and divide it by the constraint used per unit, unit contribution margin divided by the constraint used per unit, and then get the contribution margin per unit of constraint. And we're doing the same thing here. I've just changed the names because now we have a different definition of contribution margin to incorporate the fact that we're not including direct labor or variable overhead in our variable costs list. And we end up with, I've changed the name here as well just to reflect the idea that it's a slightly different definition. So constrained unit throughput now instead. But the idea would be you'd use it the same way as in Chapter 3. You'd use this number to prioritize products or anything else that is going to be using the constraint to get the biggest bang for your buck out of the constraint. And that's all I have. Bye.